started. So this is a Sidus presentation, and the topic today is how accurate are your Wi-Fi surveys, and then also does it matter? And my name is Mika Hakala, and I'm a founder CEO of Sidus, and I have about 15 years of experience designing wireless devices and software. Before this Sidus thing, I was with Hakala, head of R&D, and later CEO at Hakala. And before that, I actually did some real engineering work designing wireless chipsets. Let's get started. I'm going to show you some lessons learned along the way when we were designing this, which is the Sidus Wave, our survey device. And there's some Sidus data, because obviously I can't get any other survey device internal data except for this. But all these concepts are applicable to whatever device you're using, actually for any RF device. But if you're using some survey device today or planning to buy one, all these are applicable. So hopefully they're also interesting. So when we started designing this thing, we really were focusing on just getting the key building blocks right. So we know you're going to need a battery, you're going to need radios, you're going to need antennas, CPU, you're going to need some sort of a heat sink for heat management. And then you put everything on a printed circuit board, and you try to make it as small as possible, because small devices are cool. When you do that, obviously, parts start getting closer to each other, right? But most components don't mind. They're fine with the next component being very close. But antennas are a little different. So like this antenna here on the right, that antenna is going to hear pretty well in the direction of the green arrows. It's not going to hear well into the direction of the red arrows. Actually, even the green direction isn't very good, because signals coming from there will reflect from the heat sink, the aluminum part here, and kind of messes up the antenna pattern quite a bit. So because we are trying to design a survey device that's as omnidirectional as possible, because you want to get right measurements regardless of in what direction the AP that you're measuring is, and they're all over the place. So we want to be, good antenna pattern, as omni as it can be, okay? Intuitively, you might think that, okay, well, let's see if I can highlight stuff. Why can't I highlight stuff? Well, I'm not going to highlight stuff then. So, so the antenna on the right, if it's going to hear in that direction, and then antenna on the left, you might intuitively think that maybe that hears the other side. So let's use these two antennas to get a really good pattern, but that's not going to work. This is too long explanation for this presentation, but if you want to talk about it, just find me. So we knew all this, we were moving things around, and this is what we came up with. So with Sidus Wave, we decided to shuffle things around and put all the antennas at the top. Okay? They are clear in the top, and then we have all the metal parts, components, batteries, all the electronics at the bottom, okay? There's nothing metallic up here in the top, not even screws, okay? And there's no fan either, which is kind of cool. So we took this, of course, into RF chamber quite a few times. That's what you do, and phenomenal results, as you would expect, right? But that's not enough. This device needs to work in the real world. RF chamber is one thing, real world is another thing. So let's look at this test. So this is done in a real typical office environment, and there's an AP somewhere, and I place this device in a test rig that rotates the device 360 degrees. And it feeds the signal strength measurements and the respective angle into this polar chart on the right. And because of the test setup, the AP doesn't move, the device doesn't move, it rotates, doesn't move, so the distance remains the same. So if the antenna pattern was perfect, this would be a perfect round plot. Well, let's see. As you can see, this is 800 beacons about. It's not exactly a perfect circle, but I'd say this is phenomenally good, because this is real-world environment, okay? However, this is unfortunately not enough, because the device itself, by itself, doesn't do anything. It needs a user to go with it, okay? So in this picture, I'm wearing the device the way, we thought it's going to be in the beginning. That's what everybody does. So let's put it in a sling bag, or like a messenger bag style, or a belt clip, whatever. And I repeat the same test, except now I'm not rotating the device alone, but I'm rotating with the device, because that's the normal setup. So both of us are turning 360. And here's what the results look like. So suddenly, as you would expect, we are pretty far from a perfect circle. Okay, this is far from perfect circle. And that's because sometimes when I rotate, my body goes between the device and the AP, okay? So this is a bit of a problem. And that's why maybe you've seen me and Konstantin walk around and we're wearing, the device, what we call cytostyle, which is lift it up a little bit, and then your body is not as much on the way. And the results, not perfect circle, but significantly better. Significantly better. And let me quantify what I mean by significantly better. So here's the same tests, but now you see this green area. I hope you can see it. And this green is what the tester does. And it finds the narrowest possible band where 90% of all the samples fall. And in this case, when the device alone rotates 360, 90% of all the samples it captured, regardless of the angle, would fall on this band, which is about plus minus 1 dB. Okay? Not quite good, as good when my body. Maybe my body is special, but like when it gets on the way, if I could point things, I would show you that there's like 10 dB differences. So actually, I had to relax for the tester the requirement a little bit. So now it's 80% of the samples, and it's like plus minus 6 dB. So there's significant attenuation, as you would expect. And because the device itself does about 1 dB plus minus by itself, now we have 6. It means my torso, my body added about plus minus 5. And cytostyle, 80% within less than plus minus 3. And I bet a lot of our RF experts here and people who do real work, real Wi-Fi, they know that real world is not perfect. So if you get Wi-Fi stuff within 3 dBs, plus minus 3 dBs, you're right on the money. So this is a pretty good result. So now, this works occasionally. Well, it doesn't allow me to go back. So now here's the big question. Does this matter? Okay. So one way to look at it is something we internally use. We call it an error budget. If you do outdoor, I've ever done like outdoor, link systems, you have this concept of link budget. We have kind of similar concept of error budget. We know that when you measure things, when you filter things, when you do heat maps, when you extrapolate, you do things, all these steps introduce error. And because we want to produce the most accurate system out there, we track this error at different spots. So we know, we have an error budget, we know how much we do and how much we can introduce uncertainty in different spots. So let me show you an example. Let's say there's a signal somewhere, neg 50, neg 55. I don't know it yet, but with this design, let's say we went with our initial idea, which was kind of put everything into a small box as possible, and then wear it on a belt clip. And the antenna shadowing by some metal parts in some angles would introduce at least conservatively plus minus 3 dBs of error. And then we just saw from the previous test that my body would do about 4.71. Your mileage may vary, but like it would introduce error. So the total error margin would be about plus minus 7.71 dBs. It means that if this is where neg 55 is, if I measure it this way, or I measure it this way, this device would report for a single sample somewhere between neg 62, neg 48. Okay? When we do things cytostyle, so antennas are in the open air, they work as they are expected, and then the body attenuation is much less. Now we are within this plus minus 3 dB band that where we want to be. Now, because of this difference is so big, I dare to claim that this is more accurate device than any other device that you build and try to make it a small box and you wear it on a belt clip. And now, there may be some people who would disagree with this, but then again, to make it more than just a mere opinion, they would need to explain why antennas perform better close to metal parts and big components versus open air, or when did human body exactly become RF transparent? Okay? Or somebody might argue that, well, Mika, that might be right, doesn't matter. I wouldn't fight you on that one because you know your designs. So sometimes it's not critical, doesn't matter. Maybe you over-engineer a little bit. You throw in a few more APs than you actually need. Plus minus 3, plus minus 8, you're probably good. But then again, there are more critical situations. Sometimes you have to get it right, or as right as you can. And in general, when we were designing this and doing this error budgeting thing, we just figured that, hey, our customers are going to spend a lot of time walking and surveying. Let's give them as accurate results as we can. Okay? So another way to think about this is that because we were so accurate early in the process, capturing data, we could introduce another processing step that brings in additional 5 dBs, plus minus 5 dBs of error, and we would still be as accurate as our original idea of putting everything in a box and wearing it on a belt clip. And if you work for a big company or government, you know that if you have budget to spare, you better go shopping right now because it might be gone. But what can you buy with error budget? So let's look at this. One thing we know for a fact is that if you have less measurement points, you can have higher error. Okay? But remember, we have plus minus 5 dBs of error budget left. So what I did is an experiment here. This is an office building. I walked and surveyed as much as I could. I couldn't enter some rooms, but I tried to cover most of the space. Your typical survey, I guess. And then I did another one, which is intentionally pretty stupid, okay? I didn't walk most of it. I didn't go into any, all the rooms, even if I could. And even when I went into a room, I would start the scan, I would walk a little bit and stop. Not even scan on the way out, which is obvious, like I'm coming out of there, so I could as well scan. I did this on purpose, because I want to show you something. So, as you would expect, let's look at the heat maps. The full survey is kind of what you expect, like wherever I was able to go, I get a heat map for it. Well, the short survey is kind of what you would expect, right? I mean, you couldn't possibly send that to a customer, I presume. We do all kinds of cool stuff, or we think it's cool at Cytos, and one of them is that we have developed this AI engine. And this AI engine is able to construct digital building models out of survey information. The way it works is that you do a little bit of survey or long survey or several surveys, whatever you will, and you give that training data into the system, and it starts training an AI model and figuring out the building characteristics, okay? And because it's a generative AI, it's able to predict outcomes for situations that were not included in the original training data. That's kind of the idea of generative AI. However, we also know for a fact, because it's kind of making up stuff, it's educated guess, but it introduces error, okay? But remember, we have plus minus 5 dBs of error budget left because we did the other part so carefully. So we have this button we called Cytos AI. I just click that button and this happens, okay? So the AI fills in the blanks for me. And now if you look at the result, they're materially the same, right? So there's green in the middle, and I wish this pointer worked, but like if you look at the top right, it's kind of yellow turning into kind of orange. And then, there's in the middle towards the left, there's yellow and orange. There are also some differences. So if you look at the AP furthest down to the left, that green area and the one that's lowest to the bottom left, those green areas are a little bigger than in the AI model. And this is because this building is in Finland, and these walls are covered with windows, and they have some sort of coating or film or something. Like, it's Finland, right? You're trying to keep the winter out, good luck with that. But it reflects RF really well. So there's a lot of good multipath energy in that open space. But we kind of, made it so that the AI doesn't get to harness all of that energy. So it needs to restrain itself a little bit because some clients are not as good harvesting the multipath stuff. So substantially the same, outcome, okay? But the difference is, of course, that the one on the left was 4 times longer walk than one on the right. With the standard pace of walking, that's about 4 times longer. So I know a lot of companies would be happy if they improve their productivity by 10 or 20%. In this case, this is 362%, okay? So other cool stuff is that because we now have the generative AI model, we can ask it to produce all kinds of cool stuff. So this is a short video. So I can select an AP, I can move it around, I can delete APs, I can add APs, I can build walls, I can remove walls, I can do all kinds of stuff. And remember, this is no simulation. I don't know who did Wi-Fi for that building. I didn't have a predictive plan for it. And I didn't build one. I just surveyed. AI builds the model for me. And, I didn't select one wall and say, this is drywall, this is cinder block, this is that. The AI figures it out from the measurements. And obviously, more stuff you give it to it, more accurate it gets. If you give it just a little bit, then the error is bigger. But again, we have 3 dps of error margin, or error budget, because we do things as well as we can here. Okay? So, in summary, hardware design matters. So antennas are designed to work a certain way, but they cannot work well near metal. They just don't. The process matters. A couple 100 pounds of human will have an adverse impact on measurements. There's no way to work around it. I get it. You have some tools that you use. If you can't avoid these, and it looks too funky to wear it on the top of your helmet, I bet. So just be aware of it. You're probably fine when you know things, right? You just be aware of it. And just like I showed a few slides back, that because we had error budget left, we could survey less, meaning we have less data points. That also works the other way around. So if you're worried about the error that you are dealing with, walk more, add more stuff, walk in both directions. I remember back in the air magnet day, it's like if you walk this way and that way, things are better. So you can do that to mitigate some of the errors. And ideally, we think, this is Saidos talking, right? So ideally, we think that your tool would allow you to trade off, because sometimes you need more accuracy, sometimes you just need a quick read and be gone, right? That's what we do. So you survey as little as you want, and the AI fills the rest, or you survey everything, and then you don't need a lot of AI left because you already surveyed. Except, of course, you can do the what-if analysis. So that's what I had in mind. Just be safe out there. Remember that your survey device gives you results, and they may be better or worse at times. There's one thing I wanted to say. We are handing out 2 of these. Okay, so in your goodie bag, there's a flyer. You can scan it, or just go to saidos.com WLPC, and one is going out today, and the other one is going out tomorrow. And if you want to try it or just hear more, me and Konstantin, we are super happy to talk about it, just because he does other stuff, but this is my life. I don't do anything. I talk about this. This is what I do. Thank you so much.